All right. So, welcome to a series I want to try, um, in which all I'll be doing is really just studying math and sort of recording how that goes. And the first course I'm choosing here is going to be linear algebra. And so my goal is really just to go through like a lot of the classes that I studied in college and just kind of revisit them. And now that I'm older now and wiser and have a lot more of experience with high level mathematics, I kind of just want to go back and revisit all these things and try to make even more sense out of it. Um, and so, the name of this series is going to be called, like, I guess, LLT, which just stands for Let's Learn Together. Okay, so whenever you start a new book, you always have to look through the contents. Just sort of, it's just like an unspoken rule. I feel like that's something that I do every time. So with linear algebra, you know, you're going to be studying a lot of the same things at the introductory level, and those things are going to be kind of covered in this book. And I've chosen that book just for that reason. So hopefully, it can reach out to a wider audience. There are other books that are more abstract and they take a more generalized approach. For instance, Halmos's linear algebra is actually really good for that. I was tempted to do that, but I kind of wanted to take it even a further step back and sort of get there when I get there. I really want to go back to linear algebra when I first studied it, and maybe I'll see if I want to do that more linear algebra in the future. So why linear algebra? Linear algebra is kind of useful in a ton of places, actually. I haven't done research on like where exactly and why you'll need linear algebra. This is more of my personal experience and where linear algebra came up. The first one I think of is computer science. Okay, so computer science uses linear algebra in certain points. Don't ask me where, but I did have a friend in college who told me how excited he was to take linear algebra because of its application in computer science. So, in spirit, you can ask him because I don't know. And so linear algebra in terms of math, which I can talk about, also comes up in the study of a lot of other places. The one that comes to my mind immediately is algebraic number theory. This is like linear algebra is super used in this subject. Don't I haven't actually dove deep into algebraic number theory before, but like not in too much detail. But there are a lot of skills that you need to know with linear algebra. And so like something I would recommend someone who's like into math, who has an algebra background and a little bit of number theory. If you want to study algebraic number theory, I would suggest you just brush up on your linear algebra skills right before you start studying that. But yeah, those are the two places that I think in my life linear algebra has come up significantly. And one thing I also want to mention about linear algebra, so I'll write LA as linear algebra. It seems self-referential. And I think that's why it's useful, particularly in computer science. I feel like the study of computer science is very self-referential in that sense, especially with the stories and the anecdotes that you hear about the history of computer science. So I think I don't think it's any coincidence that linear algebra is useful there. And what do I mean by self-referential in the sense of linear algebra? Well, a little spoiler alert. the things that you do in elementary linear algebra, introductory linear algebra, turns out that the major theorems behind wrapping all that up is what you're doing is exactly like it's self-contained essentially. Like the stuff that you do throughout linear algebra, there's like the reason why you're doing it is because it is. You know, that makes no sense, but I think over time it will make sense as we dive deeper into this subject. Yeah. So, and as a quick side note, I think this is no coincidence because also category theory is also self-referential. The tools that you're using are also used on themselves. It's a little strange, but I think again, and category again is useful in computer science, and I think it's for that reason, the self-referential aspect of it. I think that's a very powerful tool, and it's something that I think we need to talk more about. But enough of that. Let us do some reading on the contents of this book. So this is Linear Algebra by Serge Lang. I've heard good things about this book, so I'm actually pretty excited to see what it's about and how it kind of flows. But yeah, let's see. So chapter 1, vector spaces. So let's look at what we have. So we have definitions, of course, bases. I do remember bases, dimension of a vector space. I think that's directly related to the base, so that's good. It's good. This is already looking pretty good. Chapter 1's looking really good. Sums and direct sums. I'm interested to see how dimension of a vector space and sums and direct sums are related. I can't remember at the top of my head, but chapter 2 is going to be about matrices. Awesome. Of course, one of the central objects of study after vector spaces are matrices. So the space of matrices, we're probably talking about like SL2Z, GL2R, things like this. Linear equations, multiplications of matrices. Interesting. Okay. Linear equations, by the way, it's funny how this comes up. And I just did an algebra video, algebra 2 video on solving linear equations. So it's pretty funny. All right. Chapter 3, linear mappings. So let's see. So of course we have mappings, linear mappings. See, I like that. I'm curious to see what that's going to be about. I think this is like the best way to introduce mathematical content is sort of, here's the general definition, and then here's what we're going to talk about, the linear versions of these. I think it's the best way to understand like general theorems and definitions. We have the kernel and the image, very standard stuff. In terms of algebra, composition and inverse of linear mappings. Okay, that's going to be interesting once again because I have not studied that in a while, so I don't even know what that is. And some geometric applications. We love geometry. Okay, chapter 4, linear maps and matrices. Oops. The linear map associated with a matrix. Okay, that I remember for sure. So every matrix is actually a linear map. Very good. So what we'll find out, but like linear maps actually transform. They transform a space into a different one and that transformation is called a linear map. Okay, the matrix associated with a linear map. Yep, exactly. So that's what this whole chapter is about. It looks like bases, matrices, and linear maps. Okay, after that, scalar products and orthogonality. So we have scalar products, orthogonal bases, positive definite case, application to linear equations, the rank. See, the rank came up a lot in algebra, abstract algebra, so that's going to be really useful to remember, to see how it was brought up in linear algebra. It's very cool. Ooh, bilinear maps and matrices. Awesome. So bilinear maps that's an example of something that you'll use in algebraic number theory. So that's perfect. quadratic forms, another thing that's useful in algebraic number theory as well. Sylvester's theorem, never seen that. I'll look forward to reading about that. Determinants, of course, this is, determinants are a, if I remember correctly, it's like a function, pretty sure. I studied category theory recently too, and I think determinants are can also be a functor. So there's a lot of stuff here. Let's see. Yeah, so we have inverses, of course, and permutations. Kramer's rule, very good. Symmetric Hermitian, I can't remember how to say that. Symmetric Hermitian and unitary operators. Okay, operators are useful in functional analysis, if I'm correct. I'll have to look that up. And then eigenvectors and eigenvalues, super good. Of course, remember those. Polynomials and matrices. Wow, there's a lot here. Triangulation of matrices and linear maps. Existence of triangulation. Cool. I think this is outside the scope. At this point, this is outside the scope of what I learned in linear algebra. So this is exciting. I think my linear algebra course went up to eigenvectors and eigenvalues. So beyond that, this is all going to be brand new to me. Exciting. Let's see. Diagonalization. That's a super important method. And polynomials of primary decomposition, convex sets, separating hyperplanes. Okay. Hopefully, that sounds super cool. I'm pretty excited about that. Iwasawa decomposition. Oh man. Okay, so this book does look really good. I'm very excited. I think for this first video, I think I'll just sort of read this first chapter introduction, chapter 1, vector spaces. All right. So as usual, a collection of objects will be called a set. Okay, so of course, I'm sure objects can have different meanings in the sense in linear algebra, but let's see. A member of the collection is also called an element of the set. Okay, so we're just introducing set theory. It is useful in practice to use short symbols to denote certain sets. Okay, what does short symbols mean? I don't really know. So for instance, we denote R by the set of all real numbers and C the set of all complex numbers. So I guess short just means like symbols. I don't know why he added the adjective short relative to the definition, I guess. Okay, to say that X is a real number or that X is an element of R amounts to the same thing. Right, okay, good. The set of all n-tuples of real numbers will be denoted by Rn. Thus, X is an element of Rn and X is an n-tuple of real numbers. Mean the same thing. Okay. Right. So I'm reading that over. That's actually pretty important here because, right, if we compare that to X just being an element of R, right, this is sort of referencing, the second sentence is referencing the element itself in Rn. So we don't say X is just an element of Rn. We're actually going to say that, well, we can, right? He's saying that that's the same. But I think it's going to be useful to also think about X being as an n-tuple, which is just like a set of numbers, right? Okay, that's really good. That's super useful information. A review of the definition of C and its properties is given in an appendix. Okay, so we remember C, complex numbers, we'll be fine without reviewing that. Instead of saying that U is an element of S, we shall also frequently say that U lies in S. And we write U is inside S, right? This is just set builder notation. If S and S prime are sets, and if every element of S prime is an element of S, then we say that S prime is a subset of S. Very good. Thus, the set of real numbers is a subset of the complex numbers, etc., etc. Okay, to say that S prime is a subset of S is to say that S prime is part of S. Yeah. I like that. I like how he actually he kind of is being a little informal here. I feel like you don't really see this a lot in books. So that's pretty cool. Observe that our definition of a subset does not exclude the possibility that S prime equals S. So that's why I think that's why mathematicians don't really write is a part of S, because how does that relate here? Right? Because someone might say like, oh, if it's a part, then it's less than, right? but not necessarily, right? Because it can be a subset can be its a subset of a set could be the set itself. Okay, but the convention that it's a proper subset, right? We add that adjective in the front to specify that it's not the set itself. Okay, so subsets will strictly mean smaller if it's a proper subset. Okay. To note the fact that S prime is a subset of S, we write S prime is a subset of S, right? We write this little like elongated C. And we also say that S prime is contained in S. Right? That's a great way to think about it, contained. It's completely inside of it, and there might be stuff on the outside. All right, if S1 and S prime are sets, S1 and S2 are sets, then the intersection of S1 and S2, denoted by S intersect S2, is the set of elements which lie in both S1 and S2, right? This is called the intersection. And we also have the union, which is the set of elements which lie in S1 or in S2, right? So you can have elements that are both in the intersection and also in the union of the two sets. So an example of that would be kind of like, let's see, let me draw S1. And here I'll draw S2. And so their intersection is quite literally this stuff in the inside. This is their intersection. Okay. And then their union will be both circles. Okay. And their intersection doesn't necessarily need to be filled, meaning they can be kind of like disjoint. Two sets could be disjoint. So if that's the case, S1 and S2, like their intersection is going to be empty set, so nothing. And that can happen. All right, so next time we'll start defining things. It looks like we're going to start defining fields. Yep, excellent. And we're going to dive right into it. Awesome. This book looks really good. Yeah, this looks very nice, the way the definitions are. Yeah, so next time we'll get into it.